Well, thanks everybody for coming. You may be less familiar with the Science Mission Directorate, so I'm providing a bit more background for you. My name is Mike Seablom. I'm the Chief Technologist from the Science Mission Directorate. And just a little bit of background. I won't go through, I've got more charts than what Jason had, but not to worry, I'm not going to go through any gory details. They're really meant to be reference for you. And just one disclaimer, a lot of the things that you see on these charts in terms of launch dates and technology readiness need dates, they're notional, they're subject to change. A lot of the missions that you see on these charts are conceptual. They represent science questions that we're trying to answer. They're also subject to change. But they represent a snapshot in time of our best guess of where we'll be going for the next couple of decades. Like Ellen mentioned in her talk this morning, the Science Mission Directorate is comprised of 4 major research divisions: Heliophysics, Earth Science, Planetary Science, and Astrophysics. Embedded in these divisions, I believe, will be some of the greatest discoveries of the 21st century. And I certainly hope that we encourage you to be a participant in those discoveries. I believe, the detection, the biosignature of an exoplanet that is like Earth won't just be a major discovery. I think it'll change everything. It'll change humanity's view of where we're going in the decade, in the century beyond this one. The detection of life in the solar system, if that happens, it could be profound. It could tell us that there's life everywhere. And during this, during our lifetimes, we have an opportunity to be part of those discoveries. So it's a great thing. What guides our direction, our science questions, we have our 4 foundational documents that I would encourage you. These can be downloaded online. They're from the National Research Council. We rely on the NRC to provide guidance on our measurements and our mission concepts. These documents represent the active decadal surveys that guide us today. The Astrophysics decadal survey will be valid until 2021. Right now, the Earth Science decadal survey team is gathering steam for a 2017 release. And then for heliophysics and planetary, early in the next decade, we'll have updates. But these are the current active decadal surveys, and they are updated. There are midterm updates every 5 years, so I'd encourage you to look at those as well. There are quite a few changes that occur in the course of these decadal surveys. If you look at the Earth Science decadal survey, for example, which was put together back in 2007, which talks about the measurement of greenhouse gases, which is so important for not only for scientific knowledge, but for policy decisions that are now being made. Not much is said about the measurement of methane, which is clearly a critical greenhouse gas. At that time, the technology was not as mature as it is today for measuring methane, so we'd expect in the new decadal there will be some changes in that regard, simply based on our capabilities, what the technology can deliver. And the other thing I wanted to mention is sometimes it's a bit perplexing on how we select our missions and how the science plan is crafted in SMD. Our missions are a combination of both strategically planned missions, which are guided by our decadal surveys, coupled with competed missions where the community basically puts their ideas forward, in terms of mission, and that satisfies the near-term demand for specific opportunities. Some examples of this, Hubble, Compton, Spitzer, LRO, the EOS Great Observatories for Earth Science were all strategic missions. And then things like COBE, WMAP, Juno, MAVEN, Aquarius, these are examples of our competed missions. The programs, the announcement of opportunities that we put forward in planetary science include the Discovery and New Frontiers, Explorers, which are our programs in heliophysics and in astrophysics. Earth Venture is a relatively new competed program in earth science, and there are others. I'll start just very quickly. Like I said, I won't go through these in any great detail. Our Astrophysics division, which is comprised of understanding our cosmic origins, how the universe operates, and also the discovery of other worlds. The strategic missions are divided up into near-term, mid-term, and then the over-the-horizon, the visionary missions. And they're selected in different parts of the electromagnetic spectrum. So going forward, the current science plan, and again, these are more representative mission concepts and not necessarily the exact missions that we'll be flying. In the near term, we have the WFIRST mission, which is mostly a dark energy mission, but we're adding coronagraph to hopefully view some of the larger exoplanets that might be possible. The technology need dates for these missions are roughly 5 to 7 years in advance of, and again, these are notional launch dates. As we go farther out beyond WFIRST, we're getting into the large aperture telescopes that will allow us to look farther back and to look at biosignatures of some of the exoplanets. And I've listed some of the key enabling technologies that we're currently invested in. And I think part of the purpose today is really we're showing you where our technology investments are currently being made, but the key message here is the science problems that we're trying to solve. And we invite you to propose other solutions to us. And perhaps you're making investments, you have technologies to solve a different set of problems that might be applicable to some of our science needs. And we welcome those ideas. And I've got some of the subject matter experts here today, but we can talk certainly offline. We can talk certainly at any time to learn what you're investing in internally in your IRADs and to determine how those might be suitable for some of our, to solve some of our science problems. We have in astrophysics 3 major strategic technology programs: the physics of the cosmos, cosmic origins, and exoplanet exploration. A lot of the technologies we invest in for the strategic missions are also applicable for the competed missions. We also have Astrophysics Research and Analysis, which is a large program that consists of not only research and analysis, but there are also technology activities there as well. So fairly large investment in technology. Pretty much everything we do in astrophysics involves new technology. And in fact, across the Science Mission Directorate, we don't really fly ordinary missions. We don't typically fly missions with off-the-shelf parts, off-the-shelf instruments. Pretty much every new technology, every new mission is involving, we're pushing the state-of-the-art to some degree. And that's why these technology programs within SMD are so important. For planetary science, we don't have a large number of strategic missions here. The focus is more on our strategic missions. The new addition going farther out into the next decade is a new emphasis on Europa. And with planetary science, we rely on our advisory groups to give us guidance on where the technology investments need to be made. For planetary science, we actually have some gap studies. These were provided by Pat Beekamp at JPL, and we work with her very closely. So we have the outer planets, we have the Venus advisory group, we have the Mars and the small body advisory groups. And for each of these areas, we don't really know what the missions will be because they typically are competed missions. We do these types of gap studies to determine where the programs need to guide their investments. And what you would expect on these charts, green should be on the left and red or orange or red on the right. Green meaning we are at TRL 6 and we're pretty close to an infusion, and then increasing the fever colors as we have more and more investments that need to be made. So one area of concern here, as you can see, the second column is the Europa lander. There's too much yellow, so that tells us we need to guide some of our investments, our near-term investments over there. So the same can be said for Mars. As we go longer term, as we go to the journey to Mars, where the humans and robotic missions start to converge, we obviously have some larger gaps. And then the same for the small body and the Venus capabilities as well. Venus becomes a big challenge when you try to put things on the surface for long periods of time to make measurements because the environment obviously is so harsh. And then our most recent guidance from the Hill is really to investigate Europa. If you're not familiar with Europa, this is a fascinating world. The fact is we've got an ice shell. It's an airless body. Under the ice shell, there's strong evidence of a deep ocean. More water is probably on this moon than there is on Earth. And there have been, there's evidence of plumes. This is a Hubble image on the bottom. Plumes of water shooting out of the body on the South Pole. So the question is there life in this water that's very likely under the ice shell? And if there is, how do we get to it? With the ice shell being as much as 10 kilometers thick, what kind of a drill would we use to get down there? Once we're down there, how do we communicate to the surface? What kind of a submarine would we use in an environment like that? The temperature is 80 Kelvin. How will we operate batteries or instruments in conditions like that? The radiation environment is as bad as it gets, pretty much. So all these challenges and guidance is to get something there in the 2020s and advanced missions probably in the 2030s. So just exciting discoveries that could be made here, but grand challenges in terms of the technology. In planetary science, we have three major technology programs. We have PICASSO and Matisse that invest in the lower and mid-TRL. And then we have the Planetary Science and Technology through Analog Research, which is a smaller program looking at things like autonomy. And then other programs that have been initiated this year, I don't have on the chart, are specific to our Europa missions, given the fact that we have a short amount of time to get a lot of work done. And then heliophysics, understanding the sun and space weather. We have 4 key strategic missions, understanding the outer heliosphere, understanding the magnetosphere, ionosphere, thermosphere system as it operates, space weather, and then understanding the Earth's extended atmosphere and how it absorbs solar wind energy. So these missions are the 4 strategic missions for heliophysics. And then this is just a listing of the technology areas that we're looking for and the notional launch dates and technology need dates for heliophysics. We have a single technology program in heliophysics. I've got $4 million a year. It's roughly 15. The number should be 15. This is the High Tides program, looking at a variety of technology areas, mostly fairly low TRL. And then finally, last but not least, is Earth science. Understanding the Earth as a complete system. We're in the process of characterizing, understanding how the Earth works as a complete system, and right now we don't have the level of detail. We have broad strokes filled in, but we need to know so much more. For example, there's missing carbon in the whole Earth system model, and where is that carbon going, and what impact would that have on global temperatures? So once we fill in that gap of the understanding, we can move to prediction. We can improve our predictions. Our predictions of weather, for example, have improved significantly because of investments, not only in the modeling, but also the technology, the computing, and other types of research. We've improved our predictive skill a day or two since I started at NASA in the late 80s. And with new missions, we can probably improve it quite a bit more with huge economic impact, with better weather forecasts. So we'll be looking at these. We have 15 strategic missions in Earth science, looking at a different portion of the Earth system, ranging from soil moisture, the SMAP mission, which is already on orbit, ICESat-2, which is looking at the cryosphere, and that's next to go. And then farther out, we're looking at the ocean topography, we're looking at ocean color, synthetic aperture radar, looking at the changes of the solid Earth, looking at aerosols, which can have a profound impact on the climate or understanding of the climate, and then going all the way out to the three-dimensional winds, that's been a grand challenge for decades now. Trying to get tropospheric winds globally has been a problem. We still don't have that. We have winds from radiosondes over land, and we infer winds from our temperature profiles from satellites, but we don't have direct measurements of winds, particularly over the oceans from space. So we group these into classes of lasers, radars, passive optical, passive microwave, and we invest in those areas on an equal footing. Earth science technology, we have a roughly $60 million a year program. In advanced component technologies, we have the instrument incubator program. And the one area in SMD where we have an information systems technology program, AIST, is here in Earth science. So this portfolio is roughly a 3-year turnaround. These are the priorities for those strategic missions, and they apply as well for our competed missions in the Earth Venture program. I want to make one other special call out for small satellites. So this is a disruption that we're. It's an opportunity, but it challenges us from a management point of view to accommodate this new capability. Probably 5 or 6 years ago, the small satellites, the CubeSats, were considered to be educational tools, or they were dismissed as maybe junk science. Nobody feels that way anymore. We see great potential in small satellites, the miniaturization of the instruments, and the growth of the platform technologies, which I would credit to not only academia, but to our colleagues in the Space Technology Mission Directorate, which have done an outstanding job in maturing the platform technologies, the thermal, the comms, the precision pointing, have given us a new capability to perform low-cost science and low-cost, very effective science. So this is an area where we need help from industry. This is an area that's changing rapidly, and we're trying to keep up. In our programs, we've, I think, done a pretty good job opening the programs up for investment in this area. And there are things that we never thought we could possibly do. So the example I've got on the screen, you see the Global Precipitation Measurement Satellite, which measures both rain and snow. We never thought, until maybe a couple of years ago, we never thought that we would get a radar on a CubeSat. But JPL, our friends at JPL have solved that problem. And using a string of pearls constellation, they've come up with RainCube, which doesn't measure the snow, but it does do a good job in the Ka band measuring radar. So the studies that we did, even in the recent past, have proven to be incorrect in determining what we might be able to do. So the technology here is moving very quickly. And sometimes in the government, we lack the agility to respond to these things quickly, and that's where we think industry could help. And it's not just earth science. I should point out that in astrophysics, and especially heliophysics, and I've got Dan Moses here, but looking at large numbers of measurements could really help us. And heliophysics, the instruments, are amenable for miniaturization in many cases. Planetary science, we've got Marco, which is a comms demonstration of communications satellite. So, and for planetary science, we're looking at daughter craft to complement some of our larger missions. So we've got all kinds of possibilities, and I think there's a lot of room for collaboration. So finally, I think these were provided to you. These were our problems, our challenges. I listed one from each of our divisions, and then I added a computational challenge, which I think is cross-cutting. For astrophysics, we have a long-term goal of achieving unprecedented exoplanet science, and we're talking about large apertures. We're hearing as much as 16-meter apertures, which would be very difficult in terms of suppression of vibrations, assembly in space, if that's necessary, the mirror coatings. All of these are, the starlight suppression. These all represent challenges for us. And then I listed our current approaches, how we're planning to tackle these. These aren't the answers. These represent our current investments, and we're asking you to add to the list if you can. In earth science, we're having difficulty measuring some of our atmospheric chemistry and our tropospheric winds, like I mentioned. That's typically done, our current approach is with lasers. There may be other approaches. In fact, for the winds, we've gotten proposals to look at other approaches that would greatly reduce the cost. In heliophysics, they've wanted swarms of satellites, of CubeSats, for a long time, but the management of an observation system like that represents some problems. So we're looking for solutions in that area. And then for planetary science, life detection on other planets. So looking at mass spectrometers, looking at the microfluidics, coming up with new technies. Sometimes we don't know what we're looking for. We don't know what we don't know. And we have to approach these things with kind of a blank slate and consider all the possibilities. And then finally, the computational technology. We're at Moore's Law. We're at the end of Moore's Law, and the plateau is already becoming felt in the agency. We really hit the end of Moore's Law 10 years ago, but it was hidden by adding additional cores to the die. We can't do that anymore because we're getting bleed over from the voltages, things like that. So there's likely to be another paradigm shift toward cognitive computing, toward quantum computing, looking at ways to squeeze more performance out of our high-end systems than we're doing today, which today we're getting 10% performance out of our best applications. So 90% of the system is going to waste. When we go to exascale systems, that's just an amazing amount of computing power that is going to waste. So, how do we tackle that? And I go back to Steve Jobs, who I always admired. We have to think different, and maybe the operating systems that we're using that have been around since the 1960s, maybe it's time that we have customized operating systems for applications. That's hard. We don't have the people to do that. And would it even help? We may need some feasibility studies to do that. But the path we're on with the computing is not a good one. So we have to change course, and we could use your help. And that's all I had. I'd be happy to entertain questions.
Hi, Mike Farrer from NOAA. I'd just like to ask you, let's start at the end here with the computational technology, the things you talked about at the end. When you talk about poor performance of agency numerical models, you talking specifically partner agencies or NASA's numerical models?
NASA's. I'm not talking about partner agencies. So in NASA, we have, which might be more pertinent to you, would be our global numerical models, and those are achieving about 10% performance out of our system at Ames and at Goddard.
Right. Okay.
So.
All right. So maybe offline, I'd like to talk to you about
Sure.
the partnering aspects.
Absolutely.
Hi, Mike. Katie Coleman from OCT. So I was looking especially at the planetary things and all the technologies that you were listing needing developed, and I wondered if you think there is enough crossover. I think the answer is probably no to journey to Mars, and that sometimes I think we have a tendency to say there's planetary people and then there's human space flight, and so what are the challenges and do you have any ideas for how we could cross those barriers? Actually, today being present here being one, hopefully.
I think in the last year there's been progress made in that area. I haven't been personally involved, but I know that the management of planetary science, Jim Green and David Schur, have been meeting on a regular basis with their counterparts in HUMD and the 9th floor. And I think the plan is really, in the long term, to start bringing those together. I'm not too familiar with it, but I think the person who could probably answer that best would be Jim Green. Now, in terms of technology, we're not there yet. In terms of what technology investments do we need to be making in the long term, we're probably not where we should be. And that's probably areas where we need to do more work. And that one chart I had, the human-robotic interaction, in terms of autonomy, in terms of the computing out in the field, we're just not there yet. So it's a gap.
I might just add to that there is thinking going on about robotic precursors to Mars that not only support science but also support give opportunities for technology maturation as well as answer questions that we need to answer for human exploration. If you want to take an example from history, if you look back at the Apollo program, we know about Mercury, Gemini, Apollo, but probably less known among the public were Ranger and Surveyor. which were the robotic precursors to the moon, to answer questions that were essential to help human exploration. So the idea is in the 2020s, there are opportunities for those missions to help answer questions that are going to be essential for humans in the 2030s. You know, one example is on Mars 2020 is the MOXIE atmospheric oxygen extraction system and things like that. So we're starting to see some more cross-agency objectives put into these missions. So now that I have the mic, can I ask a question? Or can I ask a question?
Snowball only, yeah, okay.
So before I got here, I sort of remember a program called New Millennium.
Yes.
And I think they, maybe these words are not quite right, but there was a sort of blue sky meetings where people would think, you know, beyond the horizon of the decadals, what are potentially the missions we want to run and or execute, and what are the technologies that might enable those? And it was a chance to bring together the science and the technology communities. It'd probably be useful to know, and you had solicited, you know, we'd love to get your input in sort of those. What form have those blue skies turned into? Are they still blue sky meetings, or do we need to? What are your thoughts?
There are no blue sky meetings that I'm aware of. However, our chief scientist, Ellen Stoffen, is going to be challenging the advisory groups to begin looking at some of the more visionary studies. So I think they're going to be coming back, and in what form, we'll see. But under the auspices of New Millennium, I don't think they've continued. If they have, I'm just not aware of them.
In the recent past, there's been more collaboration between SMD and human spaceflight, where you'd have instruments on ISS. Where do you see more opportunities like that, where science and HEO can collaborate?
So I don't have the chart handy, but in fact, it was about a year ago I made this presentation to David. We have identified specific areas in our technology roadmaps where there are cross-cutting capabilities, and to open up partnerships for investment. So I'd be happy to send you that chart. It outlines the specific areas where we think there's overlap. There's actually quite a bit.
To add on to that, I'm Dan Bozos from the Heliophysics division, and we are licking our chops at the cislunar possibilities, just like we have from the ISS. There's a lot of good stuff we could do there.
Well, also the space weather forecasting is certainly an area that's cross-cutting, and we just did an investment with. We're partnering with the Space Technology Mission Directorate to enhance some of the space weather forecasting that would benefit human exploration.
I don't know if this is the chart you're thinking of, but I remember in trying to figure out what would robotic precursors be, there was a chart that would say that pointed out all the things we've already learned through science, through Planetary, a lot of it through Planetary, about that support the human mission. The orbital environment, you know, what's the radiation environment? How do we maneuver around low gravity bodies if we want to go to Phobos and Deimos? Atmospheric entry information that we've already learned from the various landers and rovers, and then surface mobility, hazard avoidance, you know, the makeup of the atmosphere and the surface and so forth. So there's actually, I think we've done perhaps a little bit of a disservice not communicating how many things we have actually learned already. Deep space communication, navigation, I mean, the list goes on and on, but there's still things we need to learn. And it would probably be good to advertise what we've already learned.
Yeah.
And it's a lot, and a lot of it from Planetary, yeah, most of it.
And I'll just say, you know, having the Space Technology Mission Directorate as kind of a agnostic entity, it allows for better cross-pollination of some of these technologies. Okay. All right, well, thank you very much. Appreciate it.